Hey, so welcome back, and this is another daily code problem. So today it's called maximum score after n operations, and it's a hard level dynamic programming problem. And so basically you're given an array here with a list of like n different numbers, and you want to calculate the maximum score that you can receive after like n operations. Now, at every step, an operation is basically you select any two numbers within the array, can be like at any index, and you want to take the greatest common denominator of those two numbers. And to do that, like if it's an easy level problem, typically you have to actually like write out the code to implement it. But in this case, since it's a hard level problem and the whole point isn't really to create that or to like create that method, you can just import from the math library, like the actual greatest common denominator function. Okay, so from there, you want to actually multiply at every step once you calculate the greatest common denominator between those two numbers. You just multiply it by the current operation that you're on, and it starts with 1. And so when you, say if you grab 1 and 5 in this case, 1 and 5, you calculate the greatest common denominator, then you multiply it by 1, since that's the first operation that you just did. But when you grab the second pair of numbers, say 2 and 4, then you multiply it by 2. When you do the next pair, you multiply it by 3, and so forth. And the only other thing that you have to realize here is once you use like two numbers, you can't use them again. And so then you're forced to select a second pair, like 2 and 4, and then you're left with just 3 and 6. Okay, so once again, we want to calculate the maximum score. So this is a maximization problem. Now, this is going to be used with like dynamic programming, because if you don't actually implement any caching, this will actually end up becoming like an n to the exponent n solution, which is very, very bad. It's pretty much as bad as you can get. But with using caching, what you can get is first the greatest common denominator function runs in log of the maximum of those two numbers, like say I and j. So that's the time complexity of this method here. But then you also want to multiply it by n squared. And you get n squared because that is the number of pairs that you can have in an array of size n. So you want to calculate, and you're going to have to calculate all the different possible combinations that you can make in this array. But then you're also going to have to multiply this time complexity for a 2 to the exponent n. And that's because at every step of these operations that you're going to have two choices. And that's kind of like you're basically creating a decision tree where for the height of the tree at every step, you're going to have two different decisions. And those decisions are, I can either include this number in my greatest common denominator calculation, or I can say I don't want to include it. Okay, so this is actually the time complexity that we're implementing, which is huge. It's a huge time complexity, but it's just a very complex problem, and so you're forced to have this. So yes, let's go ahead and implement it. We are going to also import from the collections library the default dictionary method, and that's going to be used so that we can have our O of 1 like lookup using a hash map. So let's go ahead and have that. So we can just call this cache, and we're going to call this, or we're going to use that default dictionary with an integer. And so that's going to be a bitwise key that we're going to implement, where it will be something like this, where for this particular array, say at this step here, at this point in time, we will have used just two numbers so far. And so our key is going to look like 1 0 0 0 1 0. And what this represents is that the zeros mean we haven't used it so far, and the ones mean we have used that number. And so all that's happened so far is we've used 1 and 5. And so the number 1 here for the first index just represents, okay, we've used this number. And then for number 5, we have a 1 to represent that we've used that number. Okay, and so this is just used to uniquely define or uniquely identify at this particular like permutation, we can have this maximum score. Okay, and so by using like a bitwise way, it's just very simple to uniquely identify like this particular permutation or choice that we've made. Okay, and so we're going to want to return the result of our like DP top-down approach, and so we're first going to want to pass in 0, which will be the start of our bit mask that we're going to have. So initially, none of these have been used, so it's basically 0, 0, 0, 0, 0, 0. And then from that, we're also going to want to have 1, and 1's going to represent the current operation that we're on, and we're starting at 1 since it's 1 indexed. Okay, so let's go ahead and define that function. Call it DP, and we're going to first say bit mask, and then the OPs just represent the operation that we're on. And so typically the first thing that you're going to want to do for this memoization approach is you just want to see, have I already pre-computed this particular step? So we just say, okay, if this particular bit mask is already in our cache, then let's just return that result. Otherwise, we haven't already pre-computed this, and let's go ahead and calculate it. And so in that case, we're going to want to update our cache with the U result. But in order to do that, we want to go through all the different possible combinations, which is where we had that like n squared time complexity. And so all the combinations, that would be for I in the range of the length of our nums array. And then same thing here, we'll just use j. We want to start at I plus 1, just because you can't say use 1 and 1 when you're calculating the greatest common denominator. You have to choose 2 different numbers. And so what we're first going to want to check is that we haven't actually used those 2 numbers before. So verify I and j have not yet been used. And to do this, because this bit mask represents 1 as we've used it so far and 0 as we haven't used it so far, we can just check that bit masking to verify that we haven't used either of those numbers. And so we just say, okay, if 1 shifted I times ANDed with our current bit mask, and I'll explain this in a sec, with 1 shifted j times and then ANDed with our bit mask. And so if you're not familiar what this is, it can be definitely confusing, but basically what we're doing is, say our bit mask is 0, 1, 0, 1. And so say if I is equal to like 1 right now, or say it's equal to 2 right now. And so then we're just going to say, okay, we're going to shift 1 to like the left here 2 times. And so then it's going to be, okay, 1, move it, and then move it. And so we put a 1 here. So it's basically 1, 0, 0. And so when we do this AND operation, it just verifies that, okay, are these both 1s? No, then we put 0 here. Are these both 1s? No, then we put 0. Are these both 1s? Yes, we put 1. And so this just verifies that, okay, we're going to want to return let's see. We're going to want to turn true if these are both 1 here. And so if either of these have been used, we're going to skip it. So in this case, this represents that, yes, this particular number has actually been used before, so we're going to want to skip it. And to do that, you can just do continue. And we just duplicate this logic just because we also want to check at the jth position, have we actually used that particular number, that bit before. Okay, so from here, what we're going to want to do is calculate our new bit mask. And so if we pass this particular check, we just say, okay, in order to calculate this, we're going to want to update our bit mask to actually have those bits set as 1. And so it's very similar logic here, where we're going to shift our 1 to the left I times, and then we also OR it with our bit mask. And so this will actually update those particular bits to be set to 1. And then we do the exact same thing with J. Okay, and so from here, we're going to want to actually calculate our score that we received by having this new masking. And so it's just going to be, say score, and it's going to be set to our operation, since we want to multiply it by I, multiplied by our greatest common denominator of the number at index I and j. So we just use our nums array at I and nums at j. Okay, and so finally, all that we're going to want to do is compute the new cache result and return it. And so all that we want to do here is, at the end of this, we're going to want to return cache at this particular bit mask. I'll just move me over here. And we're going to want to calculate it. So the cache at this bit mask is going to be equal to the maximum, since this is a maximization problem, of whatever's currently at this bit mask compared to the score added with the recursive call to our function here with the new masking. And so this just says, okay, what's better? What we've already calculated, one of the different possible scenarios that we found so far, or do we want to use the new score with the new masking and see if we can get something better? Okay, and so not sure. Oh, and we will also want to increment our number of operations by 1, since this will be considered a new operation. So let's go ahead and run this. Oh, none type. So I think this DP array is returning none here. And that's because our return is within this for loop, but we want to put outside the for loop. Looks good. And I think that's success. Success. So that's today's algorithm. So it's definitely a hard problem. It uses dynamic programming and bit masking and caching. So definitely challenging, and I definitely recommend looking at a few tutorials and a couple of the different solutions to figure this out. But once again, the time complexity is n squared, since we want to go through all the different possible permutations. And then we also want to multiply it by the time complexity of this GCD function, which is like log of the maximum of those two numbers. So log of max of the number at I and the number at j. And then you just, sorry about my writing, this is so bad, j. And then multiplied by, what else here? 2 to the exponent n, because our decision tree at every step, you can either include that number or not include that number in our GCD function. So yeah, I hope that helped, and good luck with the rest of your algorithms. Thanks for watching.